beads, which you can think of as each bead is built out of these twisters in some way. So it's a covariant version of the BMN light cone string, and I can try to explain that more as we go along. But at this stage, I just want to give you the overall picture. So just in sort of summary, a couple of, just to summarize this overall picture, the sigma model that we are proposing together with its gauge fixing is sort of inspired directly by the sigma model for ADS3 times S3. Though the way we do the gauge fixing here is slightly different from what we had done there, but you can apply the same procedure we apply here to the ADS3 times S3, and then, like I said, that gives you back this compactification independent sector. So that was our original motivation, or the way we arrived at it. But as I have mentioned or indicated already, two other ways in which this sigma model is very natural when you consider n equals to 4 super Yang-Mills is the fact that it's very closely related to this BMN light cone string theory, and the fact that you can also the sigma model is very close to the open string theories, the twister open string theories that people have proposed for super Yang-Mills scattering amplitudes. So the theories of Berkowitz and Witten, and the ambitwister strings of Mason and Skinner. There are many points which are sort of similar. In fact, the worldsheet sigma model is a very close version of the one proposed by Berkowitz, but not identical. And it's a closed string theory we are considering, whereas people were mostly studying the open string theories here for scattering amplitudes. So these are sort of the motivations, or the sort of how this fits in with some of the other things. I just want to draw some pictures to give this idea. So like I said, this is the picture of the worldsheet, which with these W bits or beads sitting on a necklace, and the trace being the cyclic nature of this thing. And this is the time direction. So, and this is the worldsheet, if you wish. And these are non-interacting. It's a free theory. It's a non-interacting set of beads in the free Yang-Mills limit. Of course, once you turn on interactions, then you expect that there'll be interactions between these neighboring beads. But at this stage, for the free theory, this worldsheet is in some sense just has these discrete modes, these W discrete modes, and the rest of the worldsheet is sort of topological or rigid and doesn't have any dynamics. And this is another way in which you can think of this. This is very close to the spin chain picture, and that was one of the reasons to call this a covariant version, because unlike in the BMN, which was or the integrability, which is sort of fixing a certain light cone or choosing a particular large J limit, etc. Here we are not doing any such thing. And the other difference is that the individual bits are made out of these twister fields rather than the original Yang-Mills fields themselves. The underlying microscopic bits are twistorial. Something I won't really talk about is about Yang-Mills correlators. It is something which we are currently working out, which is that the Yang-Mills correlators, you can view them in the free Yang-Mills theory. So this is an example of a 4-point correlator in Yang-Mills with the double line diagrams. And the Yang-Mills correlators, in some sense, can be viewed as these rigid rods which are kind of glued together and to form a worldsheet. So now you have not, so in some sense, this is a picture of a 2-point function, so nothing really happens. But if you have, even in the free theory, if you have a higher point function, then these rods can rearrange. I mean, the beads can sort of be rearranged amongst the different operators, and that's what, in a sense, the double line diagram does. So you can actually, again, if you go by go by what we have already seen in ADS3, these Yang-Mills correlators, in some sense, give rise to world sheets, which are discrete points on the moduli space. And these discrete points are kind of fixed by something called the Strebel differential, which I don't have time to explain, but I just wanted to mention that this is very much a realization of some of the old ideas for how field theories reassemble themselves into string theories. And in the case of ADS 3 times S3, our recent paper here gave a very concrete way of seeing that. And you can see it's realized very beautifully. And there's a similar picture as we therefore expect for the Yang-Mills correlators as well. So this was sort of an extended introduction. Are there any questions at this stage about the motivation or the broad picture? Otherwise, I'll proceed on to the details.
I have a question.
Sure.
You are talking about UN supermills or SUN supermills?
Actually, it will. You will see later that in a way, the world sheet theory very naturally gives you UN, and you can, if you wish, of course, truncate it to the SUN theory. But the natural thing, in a way, that comes out of the box is a UN theory.
You said you can truncate to SUN. Is there any prescription in the worksheet side?
Yeah, that's a good question. I mean, I don't know of a very simple prescription, any simple prescription on the worldsheet side, which allows you to truncate. I mean, you can see that it's a kind of a, it's the W equals to one sector. So it's a kind of, it's the Ramond sector, and there's perhaps some way to directly see on the worldsheet how to kind of consistently truncate it. I think it doesn't sort of, if you don't include it, it won't appear in the OPEs, I think. But it is not something we have directly probed. But if you don't wish to truncate, you can look at the UN theory. And of course, you have the intuition that the SUN, the U1 part of it is sort of just overall piece. So it doesn't really propagate into the bulk. But if you wish, you can think of it as just the UN case. Okay, so if there are no other questions, let me start with the sigma model. This is something I described last time, I mean, in my lectures earlier. The sigma model, as I said, is a generalization of the ones that we had proposed for the tensionless limit of ADS 3 times S3 times T4, which corresponded to a case of NS-NS flux with one unit and the smallest non-trivial unit and no Ramond-Ramond flux. And in that case, even though the NSR description was not apparently making sense, there was a sort of a hybrid description in terms of the PSU 1,1/2 level 1 Weissmiller-Witten theory following Berkowitz, Waffer, and Witten. This Weissmiller-Witten model, just like normal SU2 level 1 Weissmiller-Witten models, because the level is 1, there's a free field description. And that free field description involved 2 fermions plus their conjugates and 2 bosons and their conjugates. And these are called symplectic bosons because that's the terminology when you have 2 bosons which are conjugate to each other and obey a first order action like a beta gamma system, but they are both spin half. So the bosons, so alpha and beta, the superscripts go from take values plus or minus. So there are 2 of these and 2 of these. So these are conjugate to each other. So 2 fermions, 2 bosons and their conjugates, 2 fermions and their conjugates. And that's the underlying theory, and you could build the PSU 1,1 1/2 generators, or rather the U1,1/2 generators at level 1 by considering bilinears of these fields. And I gave some of those details last time when we talked. But as mentioned then, you also need to quotient by an overall U1, which to get the PSU 1,1/2 at level 1. And it is this sigma model built from these fermions and bosons, symplectic bosons, that exactly reproduce the full spectrum as well as the correlators of the dual symmetric orbifold, namely the T4 to the n mod by the symmetric group in the limit as n goes to infinity. Okay, so this was the background, and now we'll consider the generalization to ADS 5 times S5. It sort of, there's a very natural generalization. You consider 4 free fermions and their conjugates, and 4 free bosons and their conjugates. So instead of two fermions and conjugates and 2 bosons and conjugates, you double the number of fields. And so now let me, this is what I had mentioned earlier, but now let me explain the notation. The lambdas and the mu's, as well as the lambda dagger and mu daggers, are the bosons. And they have indices alpha or alpha dot, which are which take values 1 to 2, and they are in the SU2 times SU2, which is a subgroup of the PSU2, 2. The SU2, 2 inside PSU2, 2/4. SU2, 2, you'll remember, is the conformal group. And so the 2 SU2s that are sitting inside SU2, 2 are the ones which we are labeling by these alpha and alpha dot. So that so the bosonic part. So this is one bosonic. The SU2, 2 is one bosonic subgroup of the supergroup. The other subgroup is the SU4, which is the R symmetry subgroup, so the conformal group, and the symmetry, R symmetry. So the other index A, which appears for the fermions, are in the fundamental of this SU4. And so you have psi A's and its complex conjugates. And here, like I said, the lambda and mu dagger are complex conjugates, so they're spin half bosons, so they're like a beta gamma system with lambda equals to half or spin half, and mu and lambda dagger are conjugates. And so this is the notation, and you can actually very naturally assemble these into what I call ambitwister fields. So so you can take the mu daggers, the lambda daggers, and the psi daggers and call them Y.
What about the indices R and S?
Oh, R and S are the mode numbers. So they will be, depending on whether we are in Never-Schwarz or Ramond, they'll be either half integer or integer.
Right. Thank you.
Right, so these are the fields, and I've written them in, decomposed them in the standard way in terms of mode numbers. But each of these fields, I can assemble them into a sort of what is called the Zs, actually, which correspond to lambda, mu, and psi, what are called twisters, and these are the dual twisters, the Yi. In fact, these were the same building blocks that appeared in the Berkowitz's open string theory for Yang-Mills scattering amplitudes. And because the bosons and fermions both have spin half but opposite statistics, and there are equal number of them, the total central charge is 0. So together, these bilinears that you can build out of these Y's and Z's, so you can take arbitrary bilinears with one Y and one Z, they generate the U2, 2/4 at level 1. This is again a generalization of what we had for U1, 1/2 2 at level 1. But now, like in that case, you have to quotient by an overall central U1 to get the PSU subgroup. And that is the central piece is the diagonal piece yi, zi. So you just take the yi, zi, that's just a sum over the diagonal piece, and you sort of set that to 0, or more precisely, you kind of, you quotient it to get the PSU 2,2/4 at level 1. And so I should mention, for those of you, I mean, some people are familiar with things coming from the twistor side, but some people might be familiar with things coming from the spin chain and integrability side, or in general, just in terms of the representations of the conformal group or superconformal group. And these oscillators, you can view them as just if you just consider, for instance, the 0 mode of these RNS to be 0 in the Raman sector, for instance, then this is nothing but the oscillator construction. So one set of these modes just give you an oscillator construction for PSU 2,2/4, and this is often what has entered into the spin chain discussions. So it's sort of the same thing, but so in some sense, these are familiar quantities, and except that now we have a current algebra version of these oscillators. Okay, so that's the difference from before. The other crucial difference is the ingredient of spectral flow that we have, which, as I said, is there in ADS3 and played a very crucial role. Because if you were not to consider the spectral flow, you would just look at the standard NS representation, where you consider these modes R and S. As I said, in the Neveu-Schwarz sector, they would be half integer moded, and you just demand that positive modes annihilate some vacuum, and you would be left with some highest weight representation. But like in ADS3, you have a lot of the non-trivial spectrum actually comes from the spectrally flowed sectors. And for those of you who remember things that I mentioned last week, spectral flow is a kind of an automorphism of the algebra, of the original current algebra, and it is reflected also in the free field realization. And it's very simple in some sense to write. It is just, this is the automorphism, that you essentially consider a new set of fields, lambda tilde, mu tilde, etc., in which the mode numbers are kind of shifted up or down by plus or minus W by 2, if you're considering W units of spectral flow. The claim is that this is an automorphism of the algebra, meaning that it preserves the free field commutation relations that I had over here. And moreover, if you look at the bilinears that are constructed from the tilde fields, they will obey the same algebra as the fields without the tildes. So like I mentioned, for the case of ADS3, this allows you to now consider new representations, which are Virasoro primary, but not highest weight from the point of view of the original oscillators or the original affine algebra. So if you define a new vacuum, which is the spectrally flowed vacuum, as one which is annihilated by positive modes of the lambda tildes and the mu tildes and the psi tildes. All the tilde modes annihilate this. But then if you view them in terms of the original untilde modes, then you see what happens is that this vacuum is a little funny, because there will be there'll be a set of modes like these, which for which only positive modes with greater than W plus 1 by 2 will annihilate it, because you just use this dictionary and demand that the tilde modes annihilate this in the usual way. Then in terms of the untilde modes, there'll be some positive modes, namely the ones between 0 and W minus 1 by 2, which are less than W plus 1 by 2. Those will annihilate, those will not annihilate this state. And similarly, there will be others which, even though they are negative modes, the ones between where R is between 0 and minus W minus 1 by 2, those will not, and those will again, so those will, when R is greater than these, then it will again not annihilate these modes. So there is something very unusual about this. I mean, you've just essentially shifted the vacuum and demanded that some positive modes annihilate it and others don't. So it's sort of, you've kind of tilted it a little bit to the oscillators. So in these, so therefore, when you consider the Wth spectrally flowed sector, you can view it as a Fock space. Now you have a free
Rajesh,
field.
I have a question.
Yes.
So in the spectral flow, how does this Virasoro generator is flowed? Is it same as ADS3 or?
Yeah, it's very similar. I have it here. I'll just mention it momentarily, but yeah, it's very similar to ADS3. So you can consider the Wth spectrally flowed sector. It's a Fock space built out of this vacuum by acting on it by now all the wedge modes, which are the modes which do not annihilate it. Well, there are these modes where R is less than minus W plus 1 by 2. Those don't annihilate it. So instead of the usual negative modes, you have there only modes which are negative beyond minus W plus 1 by 2. Now do not annihilate it. Between minus W minus 1 by 2 and W plus W minus 1 by 2, there's a set of modes which we call the wedge modes. Because in some sense you can think of a wedge in the sort of this range. As you increase W, it's growing. So if I plot R versus W, then you sort of, if I have, this is R and this is W, then I have, this is the wedge region. So that's why these are sometimes called the wedge modes, and these are called out of the wedge modes. In fact, if you look at for W equals to 0, there is, of course, it's the standard Never-Schwartz representation. But W equals to 1 is also an interesting case to consider, because there you see W equals to 1, R is 0. So you have all the 0 modes do not annihilate the, at least these 0 modes do not annihilate, half the 0 modes do not annihilate the vacuum. And the ones which are negative, these are R less than or equal to minus 1. So those will also not annihilate. So this is your conventional Ramon representation, where half the 0 modes annihilate the vacuum. And so this is also a familiar, and this is the only other case which is a highest weight representation, because anything else for W greater than 1, there will be always some positive modes that will not annihilate it, and there will be some negative modes that will annihilate it, etc. So that's and this fact that R equals to 1 and so on, these are the 0 modes, is a indication that there's some sense, and that you can think of these wedge modes as sort of generalized 0 modes. They're kind of the analog of the 0 modes that are there for this W spectrally flowed sector. And these are like the analog of the non-zero modes. All this, of course, is very similar to what was there in ADS3 times S3. It's just that we now have more fields. And so to answer the question about how the generators in the space-time are are changed by the spectral flow. I've just illustrated with some of the important ones. So the dilatation generator gets shifted by W. The R current, there's a kind of you can choose a specific combination of all the Cartan generators in the so the spectral flow kind of picks out when you do the spectral flow, you have to kind of pick out one of the directions of the R current in the SU4, and that particular R current shifts in this way. The central term, which was important, that it remains unchanged, and that's a good thing because you want the spectral flow to really act only on the PSU 2,2/4. On the U1 piece, which you're quotienting by, you don't want anything to happen, and that's what is the case. And for the Virasoro generator, yes, it is very much like in ADS3, where you might remember there was a piece which was J30 minus K30. So J30 was the space-time Mobius generator, and K30 was an SU2 R symmetry generator. But here now you have the additional piece involves, if you wish, delta, which is the dilatation generator, or D, and R, the R symmetry generator. And this whole combination is like the delta minus J that appears in the BMN story. And that's not a coincidence. And this is, of course, the original Virasoro generator. Does that answer your question, Yoongi?
Yes. Yes, thank you.
Okay. So as I said, one of the central claims which we have indirect evidence for, or we kind of are motivated, but haven't proved from first principles yet, is the claim that in a physical gauge, one can remove all the out of the wedge modes, and that there are the gauge symmetries on the world sheet allow you to remove all these modes, and you're left with only the zero modes, so to say. And so you remove all the out of the wedge modes, and you have a Fock space which is generated only by the wedge modes. This is again very similar to what happens in the ADS3 times S3 case, and it's motivated by that because there again you can frame the world sheet theory in a way that these are there's enough world sheet gauge symmetry to remove these non-zero modes or these out of the wedge modes. And if you're interested at the end, I can say more about this. But supposing we just go ahead and assume that we have only these this Fock space generated by these wedge modes. So I've repeated it again. So these are the modes which are acting non-trivially on the vacuum, and there are W of these bits. So the modes, there are W modes here for each of these fields that are non-zero. So that's the Fock space that you will consider. So you let these modes act on the vacuum. But as I said, typically there is a residual gauge condition you have to impose, and there is a remnant of the original condition that first, let me focus on this. This is a remnant of the original condition. I mentioned you have to quotient by a U1. So the modes of that U1 current, which I had called C over there, the modes which are in this range 0 to W minus 1, those are the ones which act non-trivially on these wedge modes. You want to ensure that the combination that you build out of these wedge modes is still annihilated by C, so therefore this is a very natural condition to impose or to quotient by.
Can I ask a question?
Yes.
In which sense this is a gauge choice?
which is a gauge choice? This one?
Yes.
The claim is that there is a gauge choice in which these are the physical modes. So the original worldsheet theory has, of course, these modes as well as all these out of the wedge modes. So naively, you might think that you would have to consider all of these. But of course, on the worldsheet, there are normally what do you have in flat space? You have worldsheet diffeomorphism symmetry and or super diffeomorphism symmetry, and that removes certain degrees of freedom. So the ghosts for the diffeomorphism typically remove 2 transverse degrees of freedom. So you can, that's why in a sense, go to a gauge like light cone gauge where the transverse degrees of freedom are not present in the first place. The longitudinal degrees of freedom are not present in the first place, and you can work with just the transverse degrees of freedom. So the claim is that there is something similar here, that you can use the worldsheet diffeomorphisms to remove most of these modes. So this is indeed what happens in the case of the ADS 3 times S3, because there's an underlying n equals to 2 critical string theory picture, and we claim that there is an underlying n equals to 4 critical string theory picture here. But like I said, I probably won't have time to explain that right now, but I can elaborate on that later. But
so is there like thing like Ghost that does this?
Yes, that there would be, yeah. So a full BRST quantization would involve ghosts which correspond to each of these worldsheet symmetries, and you then gauge fix in, or I mean, you can either gauge fix or you can do it covariantly. Whichever way, you effectively remove these degrees of freedom.
Okay, thank you.
I have a question when you say worldsheet description, because before spectral flow, maybe you can write down some Lagrangian in worldsheet theory, but after the spectral flow, can you really write down something like that?
I mean, it depends on what you mean by, so if you again go back to the ADS 3 times S3 case where which is reasonably well understood. You know that you can think of it either in the language, so you can think of it in the language of Hamiltonian language, in which you have these states and you're considering all these different states in the theory, and together they form the worldsheet, the spectrum of the worldsheet theory. But Maldacena and Oguri also went ahead and did a path integral quantization of the sigma model, and of course over there you can ask how do these spectrally flowed sectors come in. It was very interesting because in some sense they came about as winding modes. Where they computed the path integral on ADS 3 times S3, on thermal ADS 3 times S3, and they found that these were the winding modes, and that's how, in fact, they showed the consistency of their proposal, that the Hamiltonian picture, in which you add these different sectors, is consistent with the Lagrangian picture involving the basic original Witten model in their case, but except that you now have to include these winding sectors in the path integral. So I expect that there is something very similar over here, that you can write down a Lagrangian, even though, again, I should say, even though I said it's a free field theory, you should remember that there is this U1 current that you have to quotient by. So in some sense, you have to gauge it. So it's like a gauged linear sigma model. And since you asked, I can say that I believe that it is the sectors of this gauge field which carry non-trivial flux, which in some sense, I think correspond to the spectrally flowed sectors. So yes, I believe that there is a Lagrangian path integral picture. This is how I think it would look, but it has not been worked out.
I have a further question about this winding. Do you imagine it's winding in the light cone direction in some sense? Or
No,
some...
no, in that case, it was in the time direction, in the sort of compactified time direction. That's how it appeared in the path integral picture. Yes, but yeah, because the boundary is now was like S1 times S1.
Yeah, thanks.
Yeah. So, this is the claim that you impose this condition, and then you also impose a second condition, namely that L0, as I said, is a multiple of W. So P can be any integer when acting on the Hilbert space. And the claim is that these two conditions together are the ones that are give you the physical Hilbert space. To motivate the second one, I already motivated. It means another way to say it is that these are the C, vanishing of the C is the condition that each of the individual bits are singletons, and this will become maybe more clear a little later. The singletons are the basic building blocks of the PSU 2,2/4 representations and correspond to those letters that I mentioned in Yang-Mills theory, but we'll come to that. The condition 1 is a sort of a momentum conservation along a discretized worldsheet, which has W bits. So now you have, once you fix this gauge, you have only these modes with R taking very specific values. So if you wish, the momentum is in a Brillouin zone between -W-1/2 to +W-1/2. So momentum conservation, like in any Brillouin zone, is modulo the W. And that's what essentially this corresponds to. And that's the statement that you have a discretized worldsheet with W bits, which is cyclically invariant. Okay, so this is the motivation for these physical state conditions that we impose on these sort of physical modes that can be thought of as W bits. Is this clear? Okay, so if there are no questions, let me explain why this immediately, in some ways, gives rise to the Yang-Mills spectrum. So the way it works is that you can consider any of these. So phi I've denoted here as any of those twistor fields. It could be lambda, mu, psi, lambda dagger, etc. And you do a discrete Fourier transform. So this was the momentum mode. You do a Fourier transform to a position mode. And the positions, therefore, it's a discrete Fourier transform. So R takes values in this Brillouin zone between W-1/2 to +W-1/2. And the corresponding Fourier transform modes are labeled by a position label J, which will again take W values from 1 to W. The nice thing about doing this Fourier transform is that now when you look at these individual modes, the commutation relations are local. They just are different sites, the different modes. So now K and J label the position space, and R and S were labeling the momentum labels. J and K are labeling the positions of these twistor bits, and they commute. And moreover, you can define similarly the generator C, position space generator for the C field that you are. So that also acts locally. So here also there should have been a delta JK, which I omitted, but essentially this also acts locally. And the L0 generates a discrete translation, which is understandable because L0 is playing the role of the world sheet momentum. So e to the 2 pi I by W L0, you can just check with this definition. It just gives you, it just moves it by 1 unit, j to j plus 1. So now you can think of the two conditions that we had as instead of looking at CNs being equal from n equals to 0 to W minus 1, you can consider the combinations C hat in position space. And requiring that is saying that basically there's a singlet at each site. So we think of now the Fock space built out of the sites, and there is there's a singlet at each site, and the L0 equals to minus PW is the statement that things are cyclically invariant, because if L0 is minus P by W, then this will move sort of W times and come back to itself. So in some sense, the spectrum is that of the basic unit for one W, for W equals to 1. So W equals to 1 is, as I said, it was just the 0 modes of the, so when I wrote this, I mentioned that W equals to 1 corresponds to just the 0 modes of these oscillators. And that gives you the basic construction of the PSU 2,2/4. And the singletons are the things that you form from the bilinears of these, and they are the things, well, bilinears and other modes, but just with a single oscillator. And this is what appears in these current algebra constructions, and this gives you so a singleton essentially consists of these letters. I should have written them again, but it's these letters, a single letter. So a single letter is what is called the Singleton representation, and it is built out of these twistor oscillators. So that's part of the representation theory of PSU 2,2/4, and it's the basic building block of the representations. And so now you have W copies of these, because each of the sites, it acts as a singleton, because you impose the singlet constraint, and these sites are not talking to each other. So the spectrum is just the tensor product of the singletons, W times, but modulo this condition, which is the cyclic invariance. So it's the singleton modulo cyclic invariance, and that's essentially the reason it's the same as the single trace operators with W letters, because that's also what you take. Each letter is a singleton, and you take W of them and you mod out by the cyclic group, which is what the trace does. So that's why there's a single trace acting on W letters. So if that was very fast, you can actually go, we have verified it very explicitly. And this is, for instance, a table of all the free field operators at low-lying levels. And you can actually see very explicitly how it works. And I'll show you the simplest couple of examples on how it works. But any question?
Yeah, I have a question. Do you impose equation motion in supermass?
Yeah, that's a very good question. That's one very nice thing about this singleton representation, which I should have mentioned here. I should have probably written it when I wrote the singleton, that it is these letters modulo equation of motion. So the equation of motion is built in. When I write these derivatives here, the states which correspond to, let's say, del square phi equals to 0 in the free theory, those are automatically 0. So those don't appear. So what you get are all the letters modulo equation of motion. So the singleton construction, or this oscillator construction of the PSU 2,2/4 is very clever. It kind of knows it. It's built into it. So that's a very important point, because you are matching the spectrum modulo the equations of motion. Okay, so let me quickly speed up since I'm running out of time. To organize the spectrum, firstly, there's a very nice thing already, because in some ways, and I will illustrate it in the next slide, the Yang-Mills spectrum can be organized in terms of the L0 eigenvalue. Which is not something you have in the Yang-Mills theory. It's a worldsheet construction, this L0. And there's a nice way in which you organize it by L0 eigenvalues. It's a bit like the BMN construction again, but now for the whole spectrum. And there's a very nice sense in which I think the L0 eigenvalue stratifies the spectrum in some very nice way. And moreover, there are these, like in the old string theory, there are these so-called DDF-like operators. The DDF operators were sort of spectrum generating operators in the old string theory. And there's an analog of them here as well that you can build from bilinears of these Y's and Z's, but now with non-zero modes and in the wedge. What these do is they map the reduced oscillator Fock space, this wedge mode Fock space, onto itself. They also commute with the C's because they are sort of neutral. And in fact, the simplest case where M is 0, the zero mode of these generators realizes the global U2,2/4, and of course, once if you act on a singlet state, it will preserve the singlet condition, and therefore furnish representations of the global PSU2,2/4. So in some sense, you're assured that you will get things which are complete multiplets of PSU2,2/4. So in particular, you can start with this vacuum state in the W spectrally flowed sector, and the Sij zeros, if you act many of them, they generate the whole representation. And since this had L0 equals to 0, and this has a mode number 0 here, L0 will continue to be 0. And this, in fact, generates a whole representation of PSU2,2/4. And what is this representation? It's nothing but the BPS representation. So remember that there's a half BPS representation in n equals to 4 Yang-Mills, which is sort of a scalar in the space-time direction. So that's what these two indices are, the SU2 indices in space-time, but transforms in SU4 in the sort of W symmetric representation. And roughly speaking, they correspond to trace phi I, phi j, phi k up to W in the symmetric traceless representation. And these are half BPS states, and they're protected actually in the interacting theory, and they correspond to the supergravity Kaluza-Klein multiplets in the ADS 5 times S5. So you see these are a very nice set of the spectrum. They are just the ones which correspond to L0 equals to 0. In fact, these seem to be the only physical representations with L0 equals to 0. So L0 equals to 0 truncates to just the BPS sector. That's like in BMN, it's like the light cone vacuum. This is like the analog of the light cone vacuum, but now for finite W. And because remember, this W is now, for this plays also the role of the R symmetry current. So this is this multiplet is the BPS multiplet, but you can consider others. And in fact, if you have to go beyond W equals to 1 to see this. So let me illustrate it quickly. W equals to 0, there was only the Never-Schwarz vacuum, and that corresponds to the identity operator in superunions with 0 letters. So that's very natural. When W equals to 1, there is you get a single letter. So it's the BPS thing, BPS representation with corresponds to the singleton. And as I mentioned earlier in response to the question, this is absent in a SUN gauge theory, but is present in a UN gauge theory. Things start getting interesting from W equals to 2 onwards, For L0 equals to 0, we have the analogous BPS representation I mentioned earlier. That's the stress tensor multiplet given by this. But there are others. Now you can remember L0 must be just a multiple of W. So for L0 equals to -2, there's a very nice representation. You can see this by looking at defining this state, which is the spectrally flowed vacuum. And you act by, now there are only positive plus half modes of the W equals to 2. The mode numbers just go to plus minus half. So the plus half modes give you just, there are 4 fermions, so you can only have this state. And this is, in fact, what is the highest weight state of the Konishi multiplet, which is a singlet under SU4. So unlike this case, which was symmetric traceless, this one is the trace part, in fact, of the trace phi I, phi j. So this is the highest weight state, and you can think of it in terms of the spectrum generating algebra as produced by the +1 modes of the DDF-like operators. But you can consider other values of L0, other even values, and those actually correspond to this Konishi operator, but now you act on it by plus half modes of the bosons. And that generates all the physical states with L0 equals to -2p, and together with, of course, the PSU 2,2/4. So this is the highest weight state. And these now carry labels in space-time because the bosons carry the labels in space-time. So these are in the spin p-1 representation of the space-time Lorentz group, but they are scalars in the SU4. And they correspond to the twist2 multiplets because their eigenvalue for the dilatation is 2p, but the spin is 2p-2. So they have twist2, and these are precisely the highest spin conserved currents that are there, which are in bilinears in W equals to 2. So these are, in fact, what are called the doubleton, and this is the basic multiplet of the highest spin symmetry group, HS 2,2/4. So W equals to 2, already you can see a very interesting set of non-BPS states, which include the Konishi multiplet, the highest spin multiplet, and so on. And you can go to W equals to 3, and you can work out, and as I said, you can match with this table over here, W equals to 4, etc. And the general argument that I've given should convince you that you can go on with this. So let me conclude with a sort of a laundry list of various questions one can, I think, one should address. And this is, firstly, as I said, there's a very nice reorganization of the super-Yang-Mills spectrum in terms of the worldsheet, the way the worldsheet gives it, in terms of the L0 eigenvalue. This is not something you directly see in the space-time. These DDF operators, I think, are very suggestive. Perhaps in the interacting theory, they correspond to these Yangian generators because they kind of are spectrum generating. They are not symmetries in the conventional sense, in the sense that they don't commute with the Hamiltonian, but they generate the whole spectrum. And that's sort of what Yangians also do. And so there seemed to be some possible connection between them. For that, one has to go to the interacting theory to really see that connection. The role of the higher spin symmetry, I briefly alluded to it, but this is again something one should be able to explicitly see with these generators and understand how they organize the Yang-Mills spectrum. One of the most interesting things would be to turn on the super Yang-Mills interactions on the worldsheet. And I believe that, I mean, you know now, given the spectrum matches, you know what the deformation of the theory by the interactions corresponds to. It corresponds to just turning on the Lagrangian itself, which is a marginal operator of the super Yang-Mills, a dimension 4 marginal operator. So you can consider that on the worldsheet and try to connect. I believe that it will connect with the spin chain Hamiltonian, and the integrability picture because, as I said, the zeroth order case is already like a spin chain, a discrete spin chain, but now a free spin chain. But the interactions presumably will come from just the action of the by turning on this worldsheet interaction, which will couple different neighboring spin chains, for instance. I mentioned also the connection to open string theory, though I didn't describe it, but it's one way in which I think it connects. It could connect is that the open string sector that people studied for super Young-Mills scattering amplitudes, that corresponds to some kind of d-branes in these closed strings, and presumably it has the same relation, just like these are giving you the closed string, the gauge invariant correlators, the open strings give you the scattering amplitudes. But it would be good to understand the precise connection. There are some similarities, some differences, which we don't completely understand. We see the whole Hagedorn spectrum of the string theory from the worldsheet here. So it would be good to understand how this Hagedorn transition happens from the worldsheet directly. One of the very tantalizing things is the fact that in some ways you can actually truncate to the bosonic oscillators, and the spectrum matching argument that I gave would work even for them. And so in some ways you sort of have a pure Yang-Mills spectrum is contained, is realized through these bosonic twistor oscillators. And if there's a consistent way of truncating the worldsheet theory to a bosonic theory, then in some ways you have a dual for pure Yang-Mills at zero coupling, which would be wonderful, because then you can hope to turn on interactions and understand the string theory dual to pure Yang-Mills. To translate, I think a lot of these things, one of the pressing things is to quantize from first principles, like I said, some BRST quantization with the ghosts, etc., in response to some of the question, and show explicitly that you can gauge fix to these wedge modes. This will also suggest exactly how you could potentially truncate and do turn on interactions, etc. So this is one of the very pressing questions to address here. So I'll stop there. Thank you very much, and sorry for going over time.
Thanks a lot for the very nice talk. I think there is a question from the audience.
I have a question.
Yes.
Can you think of something like a vertex operator in your approach?
Yeah. So this, again, you can ask this question for the ADS 3 times S3 sigma model in the spectrally flowed sector once again, because it's the same principle. So I think the vertex operators are, even though it's a free theory, the vertex operators, you can't write it very easily in terms of the free fields. It's a bit like writing down operators for twist fields. Even though in a free orbifold, it's still a free theory, but the twist fields are characterized more by their OPEs and not by, you can't write down a free, in terms of the free fields, you can't write down any explicit expression, but you can write down their OPEs, and that's sufficient to characterize the vertex operator, the twist fields. In fact, it is more than an analogy, I think, because in the ADS3 case, it is the twisted sector states in the orbifold that correspond to these spectrally flowed sectors. And so on the worldsheet also, I think these can be written in terms of their OPEs, and this is how we in fact computed the correlators. So the vertex operators for the spectrally flowed sectors, I think, are completely characterized by their OPEs. And that's sufficient to compute correlators of these vertex operators. So in that sense, it is like for twist fields. And I believe therefore it must be similar for the ADS 5 times S5 case.
Okay.
So hi, Rajesh.
Hi, Kim Young.
So you studied the free strings or free Yang-Mills theory, right?
Yes.
And the free Yang-Mills theory is supposed to capture also black hole entrophies. So
Yes.
can you calculate, say, some sort of partition function on these strings and get a black hole entropy?
Yeah, that would be quite, it would be, I think that's something, so first thing I should say is that what we are considering is right now is the perturbative string spectrum. Now the black hole entropy is for states which are of order n square. So of course in the free theory, there's a gradual crossover from as you build up and you have dimensions of order n squared, then you get this Hagedorn transition and so on, and you go to the black hole phase. So what we have at the moment is just a purely perturbative spectrum. So how you see states which are of order 1 over G string square, which is what n square is in this worldsheet theory, I think that is not, it's a non-perturbative, would be non-perturbative states from the worldsheet point of view. But I think it should be still possible to understand what they are. I think one should start probably with D branes, which are of order n, which are like the giant graviton states. And then probably one might be able to understand the black holes also by looking at it either as a sort of a very highly energetic excitation or some through some by in the path integral as another saddle point that appears, but exactly how it will happen I don't know, but that's definitely something very important to understand.
Yeah, but
yeah,
I was thinking about, say, zero temperature BPS black holes whose physics is captured by, and some of entropy is captured by free field theory from Yang-Mills theory perspective. So maybe from stringy perspective, you put a lot of angular momentums and charges, but still maybe you don't need to include interaction to capture that black hole entropy. Just
right.
some partition functional index.
Yeah, that would be very good to understand if there's a way in which one can actually see that. I believe that one should be possible. I mean, my intuition is what you say also, that you should be able to see it and by looking at the perturbative spectrum and it's and do some sort of a resummation of it and get the entropy. But because this is very explicit, in some sense you know what the worldsheet theory is, but you also can match very microscopically with all the states of the Yang-Mills theory. This correspondence, like I showed over here, you can just microscopically match things from the worldsheet. So it should be possible to sort of to generalize to arbitrary levels. Yeah.
Okay, thank you.
Yeah, I think there are a few more questions in the queue. Jaewon and Junggi, would you ask a question?
Yes. So like one quick question is that, so you're matching operators with Gauss law impulse, right?
Yes, exactly. Those are the single trace operators. Yeah.
So is there any way to see 1 over n in?
Presumably, are you referring to the 3-point functions, or are you referring to mixing between double trace and single trace operators? Or
yeah, I was actually thinking of the latter, but
okay. Yeah, they are kind of related, I guess. But yeah, I would imagine you would need to go to, I mean, strictly speaking, we are looking at the sphere level theory right now. You would need to, in some sense, look at correlation functions and to see the G string corrections, which are like 1 over n. So we haven't done that yet, but I suspect that in the ADS 3 times S3 case, I think the higher genus expressions, if people have seen, I mean, after our work, Lawrence Eberhardt and so on, generalized many of the things we did to higher genus, and I think it seems to work very smoothly. So I imagine in this case also it will go ahead, but it's not something explode yet.
Yeah, I suspect that what Kim Young suggested regarding this free Yang mills, in order to see the black hole state, you got to go like pretty large in terms of energy scale, like
exactly
much larger than
like
square. So
square,
that means that you might actually need to do this in order to capture black hole. So that's
but the question is that it's like a gas of free string states, and you can have very large, I mean, so of course at very large end, single string and multi-string states all mixed together. When you have highly excited states, how exactly you see that, it's still I think it's not a trivial generalization, definitely. I would say that in some way you want to see the exclusion principle from the trace relations. You want to sort of see that from the world sheet, which I think we are not seeing, which I don't quite know how you would do that yet. But that's, I think it boils down to that.
Thank you.
John Emil, would you ask a question?
Yes, thank you. A very simple question. So can you define the spectral flow on the Yangian? You mentioned this Yangian. Is there a similar automorphism for this?
Well, I mean, the question is, we haven't constructed the Yangian. We have these DDF operators, which are what we would think of as a candidate things which are related to the Yangian. So where did that go? So we have these DDF operators here, which you can construct. And here, yes, you can write down what the action of spectral flow on these are. And there is it's some generalization of the kind of things that I wrote down here for sort of generalization of these. But so you can definitely work out for these operators, and then whether that is somehow ties up with what you might expect for the Yangian, I'm not sure. I haven't thought that much about it.
I see. Thank you.
Another question from Professor Changnim An.
Rajesh, I have a question on your last comment on turning on these interactions.
Yes.
So in the super-Yang theory side, we understand fairly well based on integrability with the interactions. So now in the string theory side, when lambda is 0, you are basically describing the string theory side based on Best-Jumino-Witten model on PSU 2,2/4. Now, if we turn on lambda, then certainly all this conformal symmetry will be broken. And
no, the conformal symmetry is preserved, right? Integrably, some of the higher spin symmetry is broken. The PSU 2,2/4 is preserved in the interacting Yang-Mills theory. It is, of course, broken in the integrability, in the conventional spin because you're choosing some kind of sector and so on and so forth. But it is there in the
but certainly spectrum we know on the string theory side with the generic value of lambda. It's not conformal symmetric the spectrum. We know that actually the symmetry is not even PSU 2,2/4, but it is actually SU 2/2 square, which is actually the scattering state spectrum of the world.
That is what is manifest, but I think the whole spectrum is invariant, and it's a deformed. The generators, of course, get deformed, but there is a realization of a global PSU 2,2/4 on the Yang-Mills spectrum, because that's a global symmetry that's preserved by the Yang-Mills interaction.
Then what is the difference when you turn on lambda in string theory side?
The difference is, I think that the worldsheet sigma model is no longer a free sigma model, which translates into the fact that the underlying bits are no longer non-interacting like we had over here. But in fact, like in the spin chain, so of course, no one considered the spin, and people, they didn't really need to consider the spin chain with zero interactions because they were non-interacting. But from the worldsheet point of view, you now know how to turn on the interactions. And so that will tell you from first principles on the string theory side, how the bits must interact. And the test will be that it will give you something which in an appropriate gauge, like the appropriate sector, like this SU2/2 square sector that you mentioned, in that sector, it should reduce to the usual integrable Hamiltonian. But I think what we will get is a covariant version, because we are not breaking the PSU2,2/4.
Well, in my opinion, I think it is a Western-Witten model deformed by some marginal operators.
Yes.
This will break the conformal symmetry.
No, it doesn't have to break it. In general, it will not. For the supergroup, there are deformations that do not break the conformal symmetry. In fact, I briefly mentioned in my talk, but I didn't dwell on it. For instance, the PSU 1,1/2 Weizmann-Witten model, unlike in the usual Weizmann-Witten models for the supergroup, you don't need to have a tuning between the Weizmann term and the kinetic term. The coefficients can be individually varied, and it will still remain conformal. So it is. So the supergroups are very special, and I think something like that will happen over here as well. You can actually change the.
Then central charge of that theory is then depend both on kinetic term coefficient and level?
No, it is always the central charge is always 0 or -2 if you look at the if the U2,2/4 theory will have central charge 0, but the PSU theory has central charge -2.
Okay, thanks.
This hexagonal transition also happens in ADS3 cases that you studied.
Sorry, I couldn't hear you. Can you please repeat?
Hello.
Hello. Yeah.
Sorry, Feng Jun, could you repeat the question?
Yeah, sorry. I just wonder that does this hexagonal transition also happens in the ADS3 cases that you studied?
Yes, the Hagedorn transition happens there. There, of course, it is a little trivial because it's like the Cardi transition in some sense. It's just a modular invariance that tells you that there must be a phase the transition to the black hole state. But yeah, so you could try to understand that case. That's in some ways simpler, perhaps. But there are some interesting aspects. I think some new aspects will be there in the Yang-Mills case. But I suspect the ADS3 case will be almost guaranteed by the modular invariance. So I'm not sure whether you will be able to really see the non-trivial aspects of it.
Okay, thank you.
Can I ask one more question? Sorry for asking too many questions.
No.
So do you think is there any way to get a GLSM description for this free strings? I have in mind of this this worldsheet derivation of large N duality.
Yeah. In fact, I will be speaking a little about it in my strings in the discussion session that I'm leading. I was going to mention this point a bit, but I think it is very similar. In fact, I think it is a kind of a realization of that idea which we had proposed originally with Qumran. There are actually, it's quite amazing. There are very so firstly let me say this is also like a GLSM in the sense that I didn't write down the Lagrangian, but it's essentially you have a set of charge fields and there's under a U1 which is the one we are gauging. There's a U1 gauge field which we are gauging whose current I had written down, this field C. So you have a set of fields carrying sort of plus half charge and a set of fields carrying minus half charge. These are the basic twister-like fields. The physical fields are built out of singlets of these fields. And that's very much like in the conifold also, when you have the gauge linear sigma model for the conifold, you have set of U1 fields, charge fields under the U1. And from bilinears of these, you build up the conifold geometry. And in some ways, I think there is a similarity, especially when you go to correlation functions. You see that I think just like in that case, the theory is normally in the Higgs phase. But if you go to near the insertions of the operators, of the vertex operators, this is sort of related to the previous question you asked also about the twist field. I mean, the vertex operator, if you look at the OPE of the basic fields with the insertion of the vertex operator, so if I look at the OPE of the twister fields with the vertex operator, they have like a vortex-like behavior. So it is like each of these insertions are roughly like inserting some vortices of the U1 theory. And at the center of the core of these vortices, you have a Coulomb phase. And so in some ways, I think it is a very similar realization, but that would be very interesting to understand better. But I think that many of the ingredients are very similar. And in that paper, I was going back to this paper with Qumran after 20 years, and I was seeing we had actually written in the last paragraph that there is a gauge linear sigma model. If we have a gauge linear sigma model of ADS 5 times S5 at recoupling, we expect a similar mechanism to be there. It seems as if it is probably there, but but I think would be very good to flesh that out.
Yeah, this is very exciting. Thank you.
You're welcome.
Hey, is there any further question? Yeah, I think we've had many interesting questions and interesting lecture. Yeah, let's thank Rajesh Gopakumar for again.
Thank you. My pleasure, and hope to see you all again during the strings meeting. I hope we'll have a good meeting there as well. So all the best to all of you, and take care.